Welcome back to our channel. Today, we're diving into the fascinating world of aircraft design, a realm where science, engineering, and art seamlessly blend together. Our focus for today is on two crucial aspects of this process: stealth and aerodynamics. Stealth technology, in essence, aims to make an aircraft invisible or extremely hard to detect by radar, whereas aerodynamics is the study of how air interacts with solid objects, in our case, aircraft. These two factors play significant roles in determining the efficiency, effectiveness, and overall performance of an aircraft. However, the intriguing part is that these two aspects often have conflicting requirements. Achieving a balance between them is a challenge that aircraft designers around the globe grapple with on a day-to-day basis. It's a fascinating journey, full of trade-offs and compromises, breakthroughs and setbacks. So, fasten your seatbelts and let's take off. Stealth technology aims to make an aircraft hard to detect by radar. Now, you might be wondering, how exactly does that work? Well, it all comes down to the design of the aircraft, specifically its shape, the materials used, and even the type of paint applied. Let's start with the shape. An aircraft designed for stealth will often have a unique geometric form, characterized by flat surfaces and sharp edges. These angles are not random. They are carefully calculated to scatter radar waves in various directions, minimizing the amount of radar energy that returns to the source. This scattering of radar waves reduces the aircraft's radar signature, making it less detectable. Next up are the materials. Certain materials can absorb radar waves, further reducing the aircraft's radar signature. These materials, known as radar-absorbent materials or RAM, are often used in the construction of stealth aircraft. They can be incorporated into various parts of the aircraft, including its exterior surface and internal structures. Finally, the paint. Yes, even the paint can contribute to an aircraft's stealth capabilities. Specialized radar-absorbent paint is applied to the surface of the aircraft, further reducing its radar signature. This paint can also help to minimize the aircraft's visibility in the visual and infrared spectrums. So, to sum it all up, stealth is achieved by designing the aircraft to reflect the least amount of radar waves. This involves a combination of geometric design, radar-absorbent materials, and specialized paint. The goal is to make the aircraft as invisible as possible to radar, allowing it to operate undetected in hostile territory. But remember, stealth is just one aspect of aircraft design. There are other factors to consider, including aerodynamics, which we'll dive into in the next scene. On the other hand, aerodynamics is all about how air moves around the aircraft. It's a complex dance of forces and pressures that define how an aircraft interacts with the air it moves through. But why is it so important? Well, the answer is quite simple. Good aerodynamic design is key to efficient flight and effective maneuverability. You see, when an aircraft is in flight, it's constantly battling against the forces of gravity and drag, while relying on lift and thrust to stay airborne. This is where aerodynamics come into play. By understanding and applying the principles of aerodynamics, we can design aircraft that can fly faster, further, and more efficiently. One of the key factors here is lift. Lift is the force that opposes gravity, and it's created by the shape of the aircraft's wings. By creating a pressure difference between the top and bottom surfaces of the wing, we can generate lift. The greater the lift, the higher and longer the aircraft can fly. But lift is just one part of the equation. We also have to consider drag. Drag is the resistance an aircraft faces when moving through the air. It's like trying to walk through a pool of water. The faster you try to go, the more resistance you feel. Reducing drag is essential for an aircraft to maintain speed and conserve fuel. In addition to lift and drag, we also have to consider stability and control. An aircraft needs to maintain its balance in the air while also being able to maneuver effectively. This is achieved through careful design of the aircraft's shape, size, and weight distribution. And finally, there's thrust. This is the force that propels the aircraft forward, overcoming drag. The more thrust an aircraft can generate, the faster it can fly. This is determined by the power and efficiency of the aircraft's engines. So to wrap things up, good aerodynamic design involves considerations like lift, drag, stability, and control. It's a delicate balancing act, but when done right, it can lead to some truly remarkable feats of engineering. But here's the catch. Designing for stealth can undermine aerodynamic performance. The very features that make an aircraft stealthy can also make it less aerodynamic. Let's dive into this a bit more. Picture an aircraft designed to be stealthy. It's likely to have sharp, angular features that are great for deflecting radar waves. This helps it evade detection on radar screens. But these same features can create a problem when it comes to aerodynamics. Sharp angles can disrupt the smooth flow of air over the aircraft's surface, creating turbulence. This can increase drag, which is the resistance the aircraft faces as it moves through the air. More drag means the aircraft needs more power to maintain its speed, which can mean burning more fuel. At the same time, these stealthy shapes can also reduce lift. Lift is the force that opposes the weight of the aircraft and keeps it aloft. An aircraft with less lift has to work harder to stay in the air, which, again, can mean using more fuel. So we have a trade-off. The features that make an aircraft stealthy can also make it less aerodynamic. But that's not the end of the story. Designers and engineers have been working hard to find ways to balance stealth and aerodynamics, and they've made some pretty impressive strides. Advancements in technology and design techniques have helped to better integrate stealth and aerodynamic features. For instance, the use of computational fluid dynamics allows designers to simulate the flow of air over an aircraft's surface. This can help them find the stealthy shapes that create the least turbulence. On top of that, optimization algorithms can help find the best compromise between different design objectives. This can help designers find the sweet spot where an aircraft is both stealthy and aerodynamic. So, while there are challenges in integrating stealth and aerodynamics, it's not an insurmountable problem. In fact, it's a fascinating area of ongoing research and development in the field of aircraft design. Certain shapes optimal for stealth may increase drag or decrease lift, making the aircraft less efficient or harder to control. Let's take a closer look at a stealth aircraft. These marvels of engineering are designed with one primary goal in mind: to evade detection. They achieve this through a combination of design elements aimed at minimizing their radar signature. One of the defining characteristics of a stealth aircraft is its angular design. The sharp, flat surfaces and edges are designed to reflect radar waves away from the radar receiver, making the aircraft virtually invisible on radar screens. This is akin to a mirror reflecting light. The radar waves bounce off the aircraft's surfaces and scatter in different directions, reducing the amount of radar energy that returns to the source. However, this angular design is a double-edged sword. While it aids in stealth, it can be detrimental to the aircraft's aerodynamic performance. Sharp angles and flat surfaces can disrupt the smooth flow of air over the aircraft, creating turbulence and increasing drag. This can make the aircraft less efficient, as it requires more energy to overcome the drag and maintain flight. It can also affect the aircraft's stability and control, making it harder to maneuver. So, how do stealth aircraft overcome these aerodynamic challenges? The answer lies in advanced flight control systems. These systems use complex algorithms to constantly adjust the aircraft's control surfaces, compensating for the aerodynamic inefficiencies caused by the angular design. The use of thrust vectoring, the ability to manipulate the direction of the engine's thrust, also helps improve maneuverability. Furthermore, stealth aircraft often use composite materials and special coatings to absorb radar waves, further reducing their radar signature. These materials and coatings, however, add to the weight and complexity of the aircraft, presenting additional challenges for the designers. In summary, the design of a stealth aircraft involves a careful balance between stealth and aerodynamics. It's a testament to the ingenuity and skill of aerospace engineers that they've been able to design aircraft that are both hard to detect and capable of high-performance flight. With advanced flight control systems, the effects of the angular design on aerodynamics can be mitigated. Now compare that with this aerodynamically optimized aircraft. It's a marvel of engineering, designed with one primary goal in mind: to ensure the smoothest possible flow of air around it. Every curve, every edge, every surface has been meticulously crafted to minimize resistance or drag and maximize lift. This results in greater speed and fuel efficiency, giving us the sleek and streamlined machines that grace our skies. However, there's a flip side to this coin. The very features that make it a paragon of aerodynamics also make it stand out on radar. Its rounded contours, while perfect for manipulating airflow, reflect radar waves rather than deflecting them. This makes the aircraft more visible, if you will, to radar systems. Finding the sweet spot between stealth and aerodynamics is the challenge for aircraft designers. It's a delicate dance, a balancing act of compromises and trade-offs, but one that continues to push the boundaries of what's possible in aviation. In conclusion, while there are inherent trade-offs between stealth and aerodynamics in aircraft design, the quest for the perfect balance continues to be a driving force in aviation technology. The journey we've embarked on today has taken us through the intricate world of aircraft design, a world where invisibility and efficiency often sit on opposite ends of the spectrum. Stealth technology, as we've discovered, is all about making an aircraft as invisible as possible to radar. This is achieved through a careful selection of materials, paint, and most importantly, the aircraft's shape. The angular, sharp-edged designs often associated with stealth aircraft are not just for show. They help deflect radar waves, making the aircraft harder to detect. On the other hand, aerodynamics is about ensuring the smooth and efficient movement of the aircraft through the air. An aerodynamically optimized aircraft is designed for smooth airflow, reducing drag and increasing lift. However, these rounded, streamlined shapes can make the aircraft more visible to radar. The challenge then lies in finding the sweet spot between these two seemingly opposing design philosophies. And while designing for stealth can sometimes undermine aerodynamic performance, advancements in technology and design techniques are helping to bridge this gap. Tools like computational fluid dynamics and optimization algorithms are aiding designers in achieving a better integration of stealth and aerodynamic features. So the next time you see a stealth aircraft or a sleek, aerodynamically optimized plane, remember the complex interplay of science and engineering that goes into their design. These flying machines are not just feats of human ingenuity, but also a testament to our relentless pursuit of innovation and perfection. The world of aircraft design is a fascinating one, continually evolving as researchers push the boundaries of what's possible. And as we continue to explore this world, we're reminded of how far we've come, and yet, how much more there is to discover. Until next time, keep your eyes on the skies.